Welcome back, everybody. Today we are continuing our discussion on what we started really briefly yesterday. Cool. This was 4.3, and we are looking at Newton's third law, and I believe, was that our main bullet point? Newton's third law? No. Interaction pairs was our main bullet point. Now, we have seen this. Interaction pairs are strange because they have to act on different objects, and that can be misleading. What I mean by that is, notice the person pushes down on the box, and then simultaneously their force is acting on the box, right? But at the same time, the box pushes up on the person. So it's a different force applied to a different object. It's not from the same. It's not like we have pushing up and gravity pulling down on a single object. It's the interaction between two separate objects. Okay. Now, as we go through this, it can be kind of challenging to find these, and it just takes practice to get rolling with it. So we're just going to do a little example. Cool. A set of two forces of equal magnitude but opposite direction that act on different objects. Nice. So I'm all over the place. I got to find, here it is, Newton's third law. All right. We're jumping in with this today. Did we define? We didn't define Newton's third law. That's our start today. So here we go. Within interaction pairs is where we get this big idea of Newton's third law. And I'm going to make this all caps because it's an important one. Newton's third law. And we will just stick to convention and NTL. All right. Newton's third law. When you see this, or when you saw this rather, in physical science, I assume that it was for every action there's an equal but opposite reaction. Like, that's typically how it's presented. And that idea is okay, but we don't want to confuse it with reactions maybe in other fields of science. So we're going to get a nice formal definition, and then we'll have an easy mathematical formula to make sense of this. The force, and we're just going to use that picture from yesterday. The force of object A, and we have the picture still, so I'm just going to reference that, on B is equal and opposite. To which force? If A is pushing on B, then equal but opposite, what else must happen? Okay, not everybody at once. Angel, what happens according to this picture? If A pushes on B, like this, what else is going on here? Yeah, B is pushing up on A. So the force of A on B is equal and opposite to the force of B on A. Now, couple ways that we can talk about this, and I don't really have a primary way that I prefer, but when I have this written down, here's what I have. If we have two objects, I'm not going to draw the picture again, and we may be repeating this, but it's important enough that we do. The force of B on A is exactly equal but opposite to the force of A on B. Okay, totally. Comment I made yesterday before we decided to just abandon it and go Greek alphabet route. We are going to be using a ton of subscripts. So I will write a little bit bigger with force and stuff because we're going to have multiple words down underneath. Okay. If you are concerned about running out of paper, I can hook you up with more paper. I'd rather you write everything clearly. Cool. Now, looking at this, immediately we need to connect this idea of Newton's third law with our interaction pairs because that's the big connection that we're going to look for. So I want to do a quick example, and this is a different example than the ones we've done before. All I want you to do is to identify interaction pairs. Identify interaction pairs. All right. So, looking at this, let's say that on example A, and my pictures are going to be really lame, just so you know, and not to scale. All right. We're on a planet, I believe, and we're on Earth. So check it out without going too crazy. I'm going to say here's the top of Earth. Okay, that's like the surface we're looking at. I don't need the whole circle. Now, not at all to scale. Hypothetically, let's say that we have a table sitting on Earth. And on this table, there's a ball. Okay, gigantic table. So we'll say ball, just so it's really clear if we need it. Okay. As we look at this, here's one way that we could get misinterpreted. Are there forces interacting here? Like, obviously, right? So let's look at the ball real quick. What forces right now in this picture would you say are acting on this ball? So gravity, and I'll do a little dot diagram or free body diagram over here. Gravity pulls down. Okay, there's the force of gravity. Any other forces acting on this ball? The table. And the table's pushing up on the ball, right? Okay. F of table. Now, as we look on this, does this feel like Newton's third law to you guys? Certainly, right? The idea is like it's there, but here's my challenge for you. I want you to find me the two objects, A on B and B on A, that really and truly make this an interaction pair. And if it's not, that's okay, but I want you to identify whether or not it is an interaction pair and justify. Okay, as you're talking about that, I'm going to draw another picture on part B. The only question is this situation with this free body diagram, is this an interaction pair? Only question. Make a determination with your neighbor. I'm going to draw B as you guys are talking about it. Because it is not just opposite objects or two objects acting on each other, they're both acting on the ball. This is not a pair. And any issues if I say interaction pair with int pair? Because interaction is like a long word. Cool. We have two objects, or one object being acted on by two forces. That doesn't quite cut it. Now, if we zoom a little bit in and we just say, hey, it's on Earth, that's fine and dandy, and we look at just this part of the picture, we have the ball very clearly pushing down on the table. Now, it is a force of gravity, but now we've changed the context, right? It's not gravity just pulling the ball, it's the ball pushing on the table due to gravity. Simultaneously, the table is pushing on what? The ball. Does it flip? Ball on table and then table on ball? That's what we need. In this situation, do we have an interaction pair? We do here, and I'll make sure, because I see people that maybe still don't think so. I'm going to say yes, and I'm just going to say B for ball and T for table, okay? If we look at this, T for table, and, whoa, yeah. So this is where it gets weird because I've written this. This is the force of the table pushing up, and the force of the ball is pulling down, right? So check it out. If we wanted to write this, force of, bless you, ball on table is one of those forces, and it is equal in magnitude, equal in magnitude but opposite in direction to the force of the what? The ball on the table, or table on the ball, sorry. We have to be able to switch these back and forth to be able to clearly identify our interaction pair. Now, as we go through this, it takes practice, and it can be weird. Couple good things for you. Oftentimes, the Earth is so, negligible as far as, us causing changes in the planet that we just ignore it. Because we have such small impact on our Earth with our gravity. Maybe if we're looking at an interaction pair, it's not very interesting because the Earth is, millions and millions of times more massive than we are, that we don't have a huge impact on it. All right, as we're dealing with these, we're going to keep seeing them, we're going to keep getting practice. I have some strategies that are not like steadfast rules, but nice kind of just suggestions for dealing with these. So we're going to say strategies for interaction pairs, because our pictures and our physics is about to get a little bit more complex, not like crazy yet, but it can be hard to work stuff out. So some strategies for interaction pairs. Okay, First thing, regularly, one of our main go-to strategies is we want to separate the system that we're dealing with, which remember is the objects or object that we're acting on and the forces and the agents. We want to separate those from the external world as much as possible. So I'm just going to say isolate the system from the external world. And there's easy examples of this that we can make sense of because we do it naturally. If I were to talk about world, the force of gravity on me, who's the agent that determines the gravity that I feel right now? Earth. Now, check it out. How often do we counter in how hard the sun is pulling on me directly? Have we ever had to, when we're talking about the force of gravity, have we ever considered the sun, which is huge and certainly pulls on us because the planet orbits, but do we include it when we do our calculations with gravity? How come? Is it a big force that the sun pulls directly on us, or is it small compared to everything else going on around us? Super small, right? That external world doesn't play a meaningful role in our problem, so we ignore it when we do it. Okay, we already do it all the time. We'll see situations where maybe we need to be more specific about it. Okay, beyond this, when you draw free body diagrams, which remember FBD, when we're drawing our free body diagrams and we have interaction pairs, it is common practice, and I'll try my best to do it. I'm just going to say connect interaction pairs, which int pair. Connect these interaction pairs with dashed lines. I'm just going to say dashes. We want to make sure that we can see clearly where this actual third law is applying. Okay. Once we have our picture or our interaction pairs identified with our free body diagram, then we pretty commonly are going to use NSL, which, what is this again? Newton's second law? Dang it. What's NSL? Okay, more specifically, is there a formula for Newton's second law? Equals what? Force equals mass times acceleration. So we'll make sense of that. And then commonly, we'll use this in combination with others to find our net force. So F net. All right. And then finally, once we've found all of our net forces, we've identified our interaction pairs and all that good stuff, finally, we'll apply Newton's third law. Now, when we talk about applying Newton's third law, all I'm referencing is we wrote an equation just a second ago that I don't want to write it again because it's right above in our notes. F of A on B is equal to F of B on A. We make sure that we can just connect those. Maybe it would be helpful. I will do that. F of A on B is equal but opposite to the force F of B on A. All right. Cool. Strategies, not steadfast rules. Like there's nothing that says do this, then this, then this, because each problem is going to be a little bit different. I did not make a worksheet for us today, and I'm trying to decide the best way to do it. You guys all use notebooks, right? Nobody in here uses a binder? Okay, if I were a student and I did all my notes in a notebook and then somebody gave me a worksheet and said, here's our examples for today, it would drive me crazy that they weren't in my notes. Are you on the same page with that, or do you not care? So if I give you worksheets for example stuff, if we start doing that, you're okay if they're not in your notes, or you can take the time outside of class to put them in your notes if you want to. I also have glue sticks if anybody ever wants them. Okay, it would drive me crazy, but I'm cool with it if you guys are cool with it. Awesome. Today I don't have a worksheet. I wanted to double check on that. So we're going to use some example. We're going to do some examples today. We have one or two right now, and then we'll jump in, and I'm going to type it. We're going to use a little bit of editing magic. Now, I don't want you to get confused with this, and a couple people suggested something, but I wanted like a more thorough justification. If we didn't consider the ball pulling backward, this is gravity causing the ball to go down, right? Like, that's not the question, though. We're not just looking at the force of gravity. The ball is literally pushing down on the earth due to gravity, though. Okay, for this, it can be strange to get this up or not. Maybe it's not really odd and I just thought it was and needed this justification. So downward, we have the ball pushing on the earth. The ball is literally pushing. Like right now, gravity is causing it, but, well, if I don't push with my muscles. But I'm literally pushing on the table. Do you want to use ball on earth or B on E? Love it. I would use B on E if I were you. It's physically pushing on the earth. Okay, simultaneously, this one is the earth pushing where? On the ball. Okay, nothing crazy going on here. What should I, like, those are equal but opposite forces, right? This is Newton's third law situation. How do I indicate that this is Newton's third law? What should I connect these forces with? There's my dash line or curve or whatever you want to call it, saying, look, these two are equal but opposite. This is Newton's third law in action. Okay, the pictures I'm not always going to require, but there's going to be a point where it's going to make problems like a million times easier. Before moving on with this, any questions, concerns with what we've done here? Like, it's strange because we're changing the context a little bit, but if we're good with that, we have our picture to kind of make sense of stuff. Let's just start rolling. I need to have some known information. What do we know right now? Awesome. The mass of the ball, which I'm going to say M sub B, is 0.18 kilograms. Love it. Okay, the mass of the Earth is a gigantic number. It's 6.0 times 10 to the power of 24 kilograms. You think it's exactly 6 times 10 to the 24? No, that'd be weird if it was like a perfect number. Situations where that has happened, when people first surveyed Mount Everest, they determined it was 29,000 feet. Like, legitimately 29,000 feet, and they thought people won't believe it, so they called it 29,004 feet. Like, just a weird little thing for you. Okay, anything else? I think there is. One more thing at least. Ooh, gravity. I know the strength of gravity. Gravity, G, is 9.8, and we're going to say negative, if that's cool with you. Negative 9.8, what? We could say meters per second squared. There might be an easier unit. Newtons per kilogram. All right. Piece of cake. What are we trying to find? And I think I can do this. We're trying to find the force. Which force? The ball on what? On Earth. And I know it's tedious, but I promise the subscripts will pay off. It makes stuff look ugly for a lot of the time, but totally worth it. All right. I may be having a change in the way I want to language stuff. And apparently I can't speak this morning either. When we just say equation or equations, it makes me think that we're always going to assume that we have everything that we need and we can just plug and chug through. Is that always going to be the case? So, like, I try to get around that by saying equations and work. Do you want to stick with equations and work, or do you want to call it scratch? I'm cool with sticking with equations and work. I'm fine with just work as well, but I want you to make sure that if we call it just work, and I don't really care what you call it, just so you know, but if we're just going to call it work, still include equations that we need. Like, I need to see your equations before we plug stuff in so that if I'm trying to pick through your work, I can see if you use the right one or not. Okay. So, we're trying to find the force of Earth on the ball. Oh, sorry, ball on the Earth. Do you know the gravitational strength of our ball? I don't, not directly. I mean, maybe we do. But if we work the other way, here's what I'm thinking. Do I know there's a relationship between those two forces that we've highlighted? Like, I'm pretty sure that the force of which direction do we want to be positive. We'll commit to it real quick. Upward is positive, probably. Okay. So I know two things then. As I'm looking, the force of the Earth, or the ball on the Earth, which is what we're really looking for, is equal but opposite to the force of the Earth on the ball. Everybody on board? That's like an immediate application of Newton's third law. Which one can I start plugging into and using? I mean, either of them realistically. Do you know the mass of the ball? But again, I just want to check. Do you know the gravitational pull of the ball? Do you know the mass of the Earth? Do you know the gravitational strength of the Earth? Hey, we can plug into this one right here then, right? Because they're equal, if I solve the right side, do I get the left side automatically? For sure. So let's do that. I know that this can be looked at as the mass of the Earth times G. Everybody cool with that idea? I think so. Grab your calculators. I want to see how this goes with a calculator. Now they're getting moved around. I'm going to order a classroom set of not quite as fancy calculators. But I'll give you a second. We're going to get a gigantic number, I believe. I suppose I'll grab my calculator and see what we get so we can compare. Now, as we look at this, maybe the number is so astronomically large that it's just kind of hard to think about, I would imagine. Can somebody, do you have your work on your calculator? Can I just see how you typed it in? All right. Now, there's one little thing that maybe intentionally I wanted us to get a crazy number, because part of the problems that everybody struggles with is to see if our answer really makes sense within the context. So let's think and see with this number. This number is really big or really small. So it's gigantic, right? What we see is 25 zeros after this, which I don't even know what that number is called. It's trillions of trillions of trillions. Like, it's huge. Trillions. I don't know what that number is. If we think about what's going on here, does this answer make sense? You say yes. What did we actually just find? When we wrote it down, we said we were finding what? So careful. We're finding the force of Earth on the ball. Do you really think that as we look at how hard Earth is pushing on the ball, and there's a mistake in here, just so you know, like intentional, because it's easy to get goofed up. Is the Earth really pushing on the ball with 5.8 trillion newtons? Because if you push a ball with 5.8 trillion newtons, what happens? Probably explodes realistically, but it accelerates like way faster than you ever could. I don't think the Earth can really truly push on the ball that hard. Would you agree? So there's clearly something wonky that happened here. There's nothing wrong with this, but maybe this little part intentionally, just so we can see that this answer is atrociously big, doesn't really make sense. The Earth doesn't push that hard on the ball. So when we think about this, we need to make sure that within the context we can think about what's going on. When the Earth pushes on the ball moves. Would you agree with that? Okay, which means what's the mass that's being moved? Oh. It's the ball that's being moved, right? What did we say was being moved when we plugged in mass of the Earth times gravity? The Earth. All of a sudden, while we write it, like there's a little weird thing that happens. The Earth pushes on the ball. Don't erase it. I'm going to scratch this out, and I'm going to make a little comment because this is a common mistake that happens. As we look at this, we need to know the ball is impacted. Is being, and I can say impacted or force applied. Impact is the easier way to say this. Now, because the ball is being impacted by the Earth, we should use the mass of the ball. Now, the letters change around and it can be misleading. That's why I don't want you to erase this. If we retry this with the right value, let's just think about it. What's the mass of the ball that's being acted on? Okay, do we agree it's 0.18 kilograms? And maybe because it's written, people just don't want to give the easy answer. I need better, harder questions. All right. How hard is the Earth pulling on the ball, the object that we're looking at right now? What's the gravitational strength of Earth on the ball? 9.8. Negative or positive? Negative 9.8. Now, when I do the unit game down here and there's like no punishment or anything, how many of you guys also play the unit game underneath? Okay, I would recommend you should. I'm not going to require it, but cool. When we type in this number, let's see if this feels a little bit better. Let's check out and see how hard the Earth is actually pushing on the ball. I think it's 1.8. 1.7 what? 1.76? Okay, I'm going to call it 1.8. Okay. Now, looking at this, we have negative 1.8. We are going to come back and look at this whole equation going on then. If the force of Earth on the ball was negative of this, how could I find the force of the ball on the Earth now then? If the Earth, and I'm going to write it out again, that's negative. What did we just find the force of the Earth on the ball was? That's again a terrible question. Why did I do negative, negative? That's a better question. Yeah, equal but opposite. So when we look at this then, how hard does a ball push on the Earth? 1.8 newtons. Okay, that makes way more sense. The Earth pushes the ball with 1.8 newtons as opposed to 50 trillion trillion. Much better number. Okay, dealing with this now. Are we done? Why? What else do we need? A statement, but there's more. Read your question again. Ooh, I need to see how quickly the Earth accelerates toward the ball, right? Okay, I'm going to give you guys a second. I'm going to organize so that I can make this so it just flows through on a single line. I want you guys working together. I'm going to help you out. Do you know the acceleration? Like, we need to find the acceleration of the Earth, right? So as I'm looking at this, maybe I'll go back to the beginning and I'll say, hey, I need to know the acceleration on Earth. Is there something that we can use to relate the force that's being acted on Earth, the acceleration, and the mass of Earth? Whose law? Which law, rather? Second law. Apply Newton's second law in this context. Find me the acceleration of Earth. Chat with your neighbors. I'll come around and get help or give help if needed. Now, one little thing that you'll notice is different as we go through this. Your book likes to use this idea of net force. But remember, they're not canceling each other out at the same point, so the ball is still pulling the Earth up. Okay. What are we going to plug in for this force? What was the force at the 1.8? Newtons. Okay, and I'll do newtons here. Over, what's the mass of the Earth? 6 times 10 to the 24. Okay, on your calculators, do you agree that sometimes it's kind of gross to use times 10 to the 24? Like sometimes it just kind of sucks to write out. So I'm going to show you guys a handy thing that we can do. On our calculators, 2 ways you could type this in. If you wanted to, we could certainly do 1.8 divided by 6.0 times 10 to the power of 24. That works. Okay, we get this number. Do you guys get the same number? But check this out. I'm going to show you guys a shortcut because scientific notation will show up fairly often in here. If you look above the comma button, which is directly above 7, what's written in blue? EE. Okay, exponential. If we just do 6e to the 24, second comma will get us this button. We get the exact same thing. We can save the times 10 to the whatever power. Did you get the same thing? Okay, last little piece then. We now know the acceleration is gigantic or tiny? Careful, it's 3 times 10 to the what power? 24, 25. Okay, I don't want to write it out, but that's 0.000000000000003. Is that really big or really small? 0.00000. Oh, really, really small. Almost nothing. Would you agree with that? In the grand scheme of things, is this essentially just negligible? Not even worth considering because of how small this number is. Tiny. So let's write our one statement, and this is where we're going to end today. The ball pulls Earth, in capital E, or pushes Earth rather, because we're not looking at the gravitational impact, pushes Earth with 1.8 newtons of force and the Earth, and there's 2 ways we could word this. I know how I would word it. We could say the Earth accelerates at 3 times 10 to the negative 25 meters per second squared. Alternatively, that's pretty close to what? I'm going to keep you guys for like 30 extra seconds. Is 0.00000 all the way down? That's pretty close to what number? The Earth essentially sits still. I would like to see your values still, but if we're this close to 0 talking about stuff, we may as well just say nothing happened. Cool. No homework tonight. If you guys are 40 seconds late or a minute late for your second hour, tell your teacher to email me. I'll have a worksheet for us tomorrow. We need to do tension.